Hi, I'm now going to prove that the normal density is actually a density, so it integrates to 1. The standard normal density is given by, as we all well know by now, 1 over square root of 2 pi exponential of minus x squared over 2 for all x on the real line. And if I want to integrate this out from negative infinity to infinity, so 1 over root 2 pi exponential minus x squared over 2 dx, then I ought to get 1. And how can I prove that this is 1? So I'm going to call I this integral, and I notice that there is no analytic closed formula for which differentiates to e to the minus x squared over 2, and therefore this integral is not given a priori in closed form. But there is an interesting trick, there is a nice trick which can help me, and that's considering I square instead of I. Now, this integral is obviously a real number, and it's obviously positive. So, because what I integrate is positive, and it's also obviously finite because exponential of minus x squared over 2 decays faster than the exponential function, so it's clearly integrable. But to get a closed form, I'm actually going to consider the square of this integral. And if I get something closed for the square of this integral, then I can just take a square root because of this positivity, so there is no problem with that. Okay, and clearly what I want to find out is that I want to find that I squared is 1. Because then if I take a positive square root, then I is going to be 1, and that's what I want to show, that this integral, this whole integral, is 1. So again, let me just put this here. How can I show that this integral is 1? Okay, so what is I square? I square is, of course, the integral from minus infinity to infinity, 1 over root 2 pi, and then e to the minus x squared over 2 dx, times the same thing. And instead of x, I'm going to use y for the second part. This integration doesn't have y in it nor x, so I can replace the integrable variable, the integration variable, by whatever I want. I want to use y here. And because everything is positive, Fubini theorem applies, so I can write this as a common integral, and I can say is the integral from minus infinity to infinity, integral of minus infinity to infinity, 1 over square root of 2 pi multiplied together twice, so that's 1 over 2 pi, and then e to the minus. Now I can join the integrands into a product, that's what I'm doing here, but I also can join the exponentials, the product of the exponentials, as exponential of the sum, and that's what I'm going to have up here. Okay, and so now comes the point in this trick. Now comes the interesting bit. So what I'm doing here is I'm integrating this function here of two variables on the whole real line. So this is an integral on R2. This integration, you could also say that xy vector is in R2. And there are different ways one can integrate on R2. One of the interesting and, in this case, very useful ways of doing it is do it in polar coordinates. Do it in polar coordinates instead of doing in Euclidean coordinates, x and y. So what are polar coordinates? Well, if you have a point xy, and of course they could also be negative, and just drawing it in the positive, and one can say that, okay, instead of parametrizing by the two coordinates x and y, one could also say that I want to find out about the distance from the origin, which I'm going to call r, and the angle from the horizontal axis, which I'm going to call alpha. And then I can easily find that x is going to be r times cosine of alpha, and y is going to be r times sine of alpha. And then if I want to find out what x squared plus y squared is, and I want to find out what dx and dy is, and what the boundary is, then I can rewrite my integral into a polar form. And that's exactly what I'm going to do. So if you look at carefully x squared plus y squared from here, then this is going to be r squared times square of cosine plus square of sine, which is of course 1, so I just get r squared. And if I look at dx dy, then you could go to two-dimensional integral transform and Jacobi determinants and the like. But actually I'm going to show you a simple kind of intuitive way of at least guessing what we get. So that's actually probably a foolproof as well. So let me imagine that I want to change alpha a little bit, I want to change r a little bit, and I want to find out how does that transform into areas. These are areas, right? Dx dy, you could understand dx dy as a little area of increasing x a little bit and increasing y a little bit, and what is the area that's covered by these changes. And so I can change alpha and r and try to find out what is the Euclidean area that's covered by this. And so I can increase r by a little bit, dr, and I can increase alpha by a little bit and find out what is the area that results by these changes. What is the area covered when I increase alpha by d alpha? Obviously this is not a precise formulation what I'm doing here, but you can make this precise, or you can just go to the Jacobi determinant formalism. But anyway, I think it's a very nice intuitive way of seeing it. So what can you say about this area covered in terms of dr and d alpha? Well, the thing you can say is that it's almost like a square. It's almost like a square. It's not exactly a square because you have some curved surfaces here and non-parallel sides here, but it's almost like a square of size dr and alpha times dr. This little segment here, if alpha is measured in radians, then this little segment here is radius time, sorry, this is wrong, d alpha times r. It's radius times d alpha, right? So this little segment here, this one here, is radius times d alpha. What's the radius of this arc and how much alpha changes? If alpha is measured in radians, then this is exactly that side. Now obviously this side is slightly longer, and obviously this is not a precise square, it's just close to a square. So when I'm going to say that the area is just, if I pretend it's a square, so it's going to be r times dr d alpha, then I'm committing some errors. And you can convince yourself that the errors I'm committing are small order of dr and small order of d alpha. Okay, this little notation means that if I divide this thing by dr, it still goes to 0. If I divide that thing by d alpha, it still goes to 0. And therefore, if I integrate, when I do the integration, or when I look at full areas, macroscopic, not these tiny steps, but really macroscopic areas, then even the summed up error from these terms will disappear. So I can actually replace dx dy, when I turn to polar coordinates, by r dr d alpha. That's, I believe, a nice intuitive way of doing it. Again, if you want to be somewhat more formal, then you can just go to the Jacobi determinant formulation of two-dimensional integrals. All right, so let's then proceed with this integration. And so I still have to cover all of the plane, all of r square. And for polar coordinates, if I look at the angles and the distances, then I find that I can go from 0 to 2 pi in the angle, and I can go from 0 to infinity in the radius. And so I'm going to write, instead of dx dy, I'm going to write this. So I'm going to say r d alpha. And what am I integrating? Well, it's going to be a 1 over 2 pi, and it's going to be e to the minus x squared plus y squared over 2. That's exactly r squared over 2. So x squared plus y squared turns into r squared, and so I have r squared over 2. And the alpha integration, of course, is very easy. Nothing inside depends on alpha, so it's like a constant with respect to the alpha integration. That gives me a factor of 2 pi. That 2 pi cancels with the other 2 pi in the denominator. So I'm really just end up with the integral from 0 to infinity r times e to the minus r square over 2 dr when I do the alpha integration. And now you may ask yourself, okay, how is this any nicer than the original density I started with? How is this any nicer than integral of minus x squared over 2 dx? It's almost the same. There is an extra r factor here, but as it turns out, that extra r factor helps a lot, because if you differentiate e to the minus r squared over 2, that exactly gives negative of whatever you see here. The derivative of this is the exponential itself times minus 2r over 2. So with the minus sign, it exactly gives you this this r factor in front with a positive. So all I need to do is look at this number at infinity, the limit at infinity, and the limit at 0. At infinity is 0. At 0 I have to subtract the negative of e to the 0, which is exactly 1. And so the integral square is 1, and my integral is a positive real number, so that implies that the integral itself must be 1, and the normal density, the standard normal density, is indeed a density. Okay? How do I know that the general normal density is also a density? Well, all I need to do is just go back to the probability 1 notes. I'm not going to repeat that here, but if you transform a normal, you subtract its mean, you divide by its standard deviation, you get a standard normal, and that has a density, a proper density, and one arrives to exactly this density here. So by transforming a general normal with subtracting the mean dividing by standard deviation, one arrives to here. That is a density, and due to the transformation of continuous random variables, the original normal density will also then be a density. So I'm adding this comment up here, by transforming the normal, if one has the generic normal density, so f of x 1 over root 2 pi sigma e to the minus x minus mu square over 2 sigma square is also a density, in the sense that it's also non-negative, and the integral of that from minus infinity to infinity is also 1. So that comes from transforming this general normal into standard normal by this affine transformation of subtracting the mean dividing by standard deviation.